We've talked about how many different outcomes something can have, so we're going to look at some other ways to count possible outcomes. In this way, in the first one, we're looking at how many different ways can you arrange a certain number of items in a row. So we're going to start really basic. So let's say I have the letter A. How many ways can I arrange the letter A? There's only one way to arrange the letter A, and that's just A. Okay. Let's say I have the letters A and B. How many different ways can I arrange AB? Well, I can say AB or BA. So in order, there's two different orders. So I'm to 2 now. How many different ways can I put A, B, and C in distinguishable orders? Well, it's not 3, because I could do A, B, and C, or I could switch the B and C and have A, C, B. Or I could start with B and have B, A, C, or have B, C, A. Or I could start with C and I could have C, A, B, or C, B, A. So there's actually 6 different ways to put A, B, C in distinct orders. Now what about A, B, C, D? Now at this point you might think, I don't know that I want to list all of those. Maybe you have a guess of how many. Maybe you think it's 12. Maybe you think it's 18. Maybe you think it's, who knows. You have some sort of guess of, maybe you think it goes up by 1 plus 1 plus 4, maybe plus 6 or something. But let's think about this in a way that maybe we won't have to count them all. So let's just look at ABC. And let's say I wanted to include D now. So where could I write the D? Well, I could write A, B, C and put the D at the end. Or I could say A, B, put the D next, and then put the C at the end. Or I could write A, put the D as the second number, or second letter, and then put B, C at the end. Or I could put the D first, D, and then A, B, C. So for just that one first order for A, B, C, there's 4 different places I could include D. So for each of these 6 orders of A, B, C, I could put D in 4 different places. So I'm going to have 6 times 4 different arrangements of 4 letters, or 24 arrangements for 4 letters. Okay, so 24. Now, what can we conclude from all this? Well, I want you to think about a pattern that we can see here. We start out with just 1, okay? And then we think, well, for that letter, there's 2 different places I could put B. So it's 1 times 2. And then there's 3 more ways that I could put C in for every place there's A and B. So this is going to be 1 times 2 times 3, which is 6. And then you see that to get from 3 things to 4 things, there's 4 ways I can put in D for every one of the arrangements for 3 letters. So now this is 1 times 2 times 3 times 4, which is 24. So for 5 letters, A, B, C, D, E, there's going to be 1 times 2 times 3 times 4 times 5, 24 times 5, or 120 possible arrangements of letters. Now there's a special number or a special symbol in math that tells me to multiply like this. So how many different ways can you arrange n items in a row? It's called n factorial. That exclamation point is called factorial. So we say n factorial. You know what? That doesn't look like factorial. It looks like factorid. I'm going to write this a little better. N factorial. There we go. N factorial. So an example of n factorial, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. It just means start with this number and then multiply it by each integer going down until you get to 1. 10 factorial would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You can tell this gets to be a very big number very quickly. So this tells you how many different ways you can arrange n items in a row in a distinct order. Now sometimes I don't want to arrange all of my items, I just want to arrange some of my items. So let's say, for example, that there are 10 horses in a race. And I have no idea about the ability of any of these horses, and I want to just say, you know, I want to try to pick who's going to be the winner and who's going to come in second, who's going to come in third. So I want to know how many different ways could I get a first, second, and third place, get my first, second, and third place winners. How many different ways could the horses get first, second, and third place? So let's think about first place. Okay, so first place, I have not got, so there are 10 horses in the race. So any one of those could be first place, assuming they're all of equal ability. I have no idea what their ability is. Now second place, once I've gotten my first place winner, there's only 9 horses left. So there's only 9 possibilities for second place. Now for third place, I've already gotten my first and second place winner, so there's 8 horses left. And remember we talked about when we have different events, the event that we get first place, second place, and third place, we multiply those probabilities. This is 720 possible first, second, and third place orders. Now you might recognize this as the fundamental counting principle. So that's exactly what this is. This is just the fundamental counting principle. If we know how many ways each event can occur, then we just multiply them together if they all occur. So the fundamental counting principle. But it also has another special name, and it's called a permutation. A permutation. So I'm going to put this up in the box. How many different ways can you arrange R out of n items in a row? And this is called a permutation. And we write it like this. N, the permutation of n select R, is n factorial divided by n minus R factorial. So let's apply this to our horses. So for our horses, if we do NPR, the N is going to be the 10 horses, and the R is the 3 horses that I'm picking for first, second, and third place. So I would write 10 P3. So this would be 10 factorial in the numerator, and in the denominator, 10 minus 3 factorial. So if I expand my 10 factorial, I would get 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. In the denominator, I have 7 factorial. I probably should have written that as a separate step. So let me kind of scoot this over. I know you're probably going crazy with this, but I'm going to scoot this over. And you can kind of squish this in however you want to. So this is 10 factorial over 7 factorial. All right, so if you just want to write underneath there 7 factorial and then point to over here, that might be nice, but I wanted my notes to look nice. So this is 7 times 6 times 5 times 4 times 3 times 2 times 1. Now you'll notice when you divide here, 7 divided by 7, 6 divided by 6, 5 divided by 5, all of these just equal 1. So I can divide out any of the common factors in the numerator and the denominator, and I'm just left with 10 times 9 times 8, which is exactly the same that I had before. So using the permutation rule, is kind of optional. You can always just use the fundamental counting principle. So this formula is not always necessary. You could figure this out without it. So but I'm showing it to you because this formula leads to a couple of other formulas that are essential to use. So I don't really need the formula for permutations. I can figure out how many ways to put something in order just using the fundamental counting principle. But what happens if some of the items in my list that I'm choosing from happen to be repeated? So let's say I have the letters A, B, and B instead of A, B, and C. So I have two B's. And I'm trying to find the number of different ways I can arrange these letters. Well, if I switch the two B's, there's no difference. So that's not very helpful. But I could put the B in the front, then an A, and then a B. Or I could put two B's in front and then the A last. But it only leaves me with 3 different arrangements instead of the 6 that I had before when I had A, B, and C. So what's happening here is switching the B's doesn't make any difference in the way the sequence looks, so it's not distinguishable. A, B, and B, and I switch the B's, same thing. So let's look at a more complicated example. Let's say we have A, B, B, C. How many different orders could I arrange this in? Okay, so obviously if I move the B's and the C's around and put them in different orders, there's a lot of different arrangements I could make. But just switching the A's around doesn't do anything, or just switching the B's doesn't do anything. So here's how I would figure this out. Number one, I have 6 letters. For A, it's repeated 2 times. No, sorry, 3 times. A is repeated 3 times. B is repeated 2 times. Okay. So the way I'm going to write this is in the numerator. I know the number of ways I could arrange all 6 letters would be 6 factorial. So in the numerator here, I'm going to write 6 factorial. But I'm going to divide it because I know that there aren't 6 factorial different unique ways to arrange this because the A's and the B's are repeated. So I have to divide by the number of ways that I could arrange the A's. So how many different ways could I arrange 3 letters? 6. But all 6 would look the same. So 6 is 3 factorial. So I am going to divide by 3 factorial. This divides out the 6 different ways that I could rearrange the A's because they don't make any difference. How many ways can I arrange the 2 B's? Well, that's 2, or 2 factorial. So this is going to be 2 factorial. Now I could say C only can be arranged one way because there's only one of them, and I could put a 1 factorial here, but 1 factorial is just 1, so it's not really going to make any difference. In your book you will see the 1 factorial there. It doesn't have to be. So I'm just going to write as it's sort of optional. There's 1 C. So I could put 1 factorial here, and I'm just going to write here optional. It doesn't make any difference to divide by 1. All right. Now, how am I going to evaluate this? Well, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. And notice I don't really need that extra 1 in there. Okay, I could write it in there. It's not really a big deal. So I notice here I have a 3. I have a 2. Of course, all the 1's divide out. Don't really need them. So I have in the numerator 6 times 5 times 4 divided by 2 in the denominator. 6 times 5 is 30. 30 times 4 is 120. This is 120 over 2, which is 60. So there are 60 different ways to arrange those 7 letters that look completely different from each other. All right? It's not the ones where I'm just moving the A's around or just moving the B's around, but the entire order of the letters are switched around 60 different ways. This doesn't have a specific name for it. It's a type of permutation arrangement, but it's when you look for the word distinguishable permutations, you're going to be using this rule. So let's look at one more example just to make sure that you're good with knowing how to work this. So let's say I have a letter that has 4 S's in it, or sorry, a word. These are the letters I have. I have 4 S's, I have 4 I's, I have 2 P's, and I have 1 M. So altogether I have 11 letters. So I'm going to put 11 factorial in the numerator. I'm going to divide by 4 factorial for the S's, 4 factorial for the I's, and 2 factorial for the P's. I could also do 1 factorial for the M's if I want to. Okay, I'll go ahead and put it in there, but it won't make a difference when I divide. So multiplying this out, I'm going to have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 4 times 3 times 2 times 1 times 4 times 3 times 2 times 1 times 2 times 1 times the extra 1. All right. So let's go through and let's divide out everything that is the same in the numerator, the same factor in the numerator and the denominator. So I've got a 4 and a 4, and a 3 and a 3, and a 2 and a 2. Of course, all the 1s, I don't really need them. Okay, they're all gone. All right, so notice now I have a 6 here, and I have a 3 and a 2 in the denominator. So 6 cancels with the 3 and the 2. I also have a 4 and a 2, which is 8, and I have an 8 in the numerator. So the 4 and the 2 with the 8. So that gives me, what's left over is 11 times 10 times 9 times 7 times 5. Don't forget that 7 and 5 that are still there. That turns out to be 34,650 arrangements of these 11 letters that are all unique. Now, what's the probability that if I arrange all these letters, I'm going to get the name of a state? There's a 1 out of 34,650 chance. So, probability of spelling, do you know what the state is? Hopefully, Mississippi. The probability that I would randomly select these letters and they would come out exactly in the order Mississippi is going to be 1 out of 34,650. There's only that chance of actually getting the word Mississippi. Okay, next video then we're going to talk about what are called combinations.